All right. So you're asking me about 2.8. Um, Check for the existence, and you need also solve the following and sketch the corresponding rectangular region. Well, um, yes, you need to find D. To find D, you need to find H. Or if you don't want to use it, you can use a corollary. You know what I mean? So don't worry about it if you don't want to use. Okay, don't worry about H, but you need to find D if you want. If you, I mean, since I'm asking for D, yes, you need to find H. Okay, let's put it this way.
So the concern the three of us had is if you actually go through this, um, when you solve for M and then need to optimize B over M when you're finding H, it is
Right.
it's incredibly nasty. It's both a function of A and B. And
No, you don't
A,
need to do that. You don't need to do that. Just dominate one of them. Take
but
T less,
it's
take T less or equal to A, and A here mostly is T naught is zero here, and then take X minus X minus 3, for example, part 3, less than B, and worry about the B. Don't worry about the A.
I guess I'm confused because the resulting function, even if you treat A as a constant, it's still going to be a function of A. And so you get something that is
No,
incredibly.
as I said, you treat A as a constant.
That's what I said. But if you treat A as a constant, it still shows up in everything, and that's
Yeah,
why we were confused.
yeah, that's okay. Let it show. Let it show in everything. Okay, just take an A to be 1, for example. Okay? Just take A to be 1. So you're going to do T less or equal to 1. So that is your A. And just do it like that. Okay? And then B has to be the maximum. B has to be bigger than A. Okay? So you can do it that way if you like. Fix A and find your region. Okay? Yeah, but you need to be careful. In some places, you need to use a corollary. For the solution, they do not exist. You know what I mean? Like if you take number 4, you get x prime equal t over t squared minus 1 times x. So if you take del f over if you take f is not continuous in t, is continuous everywhere for t different from -1 and 1, right? So you know your region where it's gonna be your d, outside 1 and outside -1, or inside -1, 1. Okay. All right. So this is what I mean by d. Um, um, okay. Let me do one of them. Since we are there now, just bear with me for a second. All right. So let's take which one. Which one do you want me to do in 2.8? Do you have any preference?
2.8, problem one.
Okay, we will do one. Okay, how's that? So Just stay with me for a second. So we're gonna use the corollary. So why don't you take a quick look on corollary 2.1? Take a look at corollary 2.1. So basically, D is a subset of R cross Rn. So we want F to be continuous on D and del F over del X2. We see what this is. These are the requirement of the corollary. I think the best way to do here is use a corollary. Otherwise, things are gonna get very difficult. All right. So here, f of tx is x squared plus t over t squared minus 1. So f is continuous in t except t is different from plus 1 and minus 1. Okay? Now, what about del f over del x? That is 2x over t squared minus 1. That's again continuous in x as long as t is not equal to plus or minus 1. Correct? Okay. What else do we have for that problem? We have x of 0 equal 1. X of 0 equal 1. So that means this is t naught equals 0 and x0 equal 1. So your D is the set tx such that t, okay, now you need to look at x0 equal 1. So it's going to be t less than 1, okay, and x belong to R. Okay? So if you're going to take about the region, so your region is, this is t, this is x. This is minus 1 and 1. So your region is going to be this way, and x at, at x at 0, at t equals 0. Okay, no, this is not true. Remember, we have x of 0 equal to 1. So your region, t is less, this is not true. This is false. Because you see, you want t0, x0 to be in D. So that point to be in D. That means 0, 1 has to be in D. Okay? So it's all t such that t different from plus or minus 1 and x is in R. So I would take it like that. I want it to be 0. If it is 0, so it's gonna be this way, and this is 1, and this is x, and x at 0, D can be like this, actually. Can be like that. And here is 1. We don't want it to be. Okay? So t Okay, so if I want to do that, t belong to -1 and 1 and x in R. So now, if I take this t, so this is my d, t in -1, 1, x in R. So your region is going to be like this, -1, 1, and we're going to have, okay? And then this is your point 0, 1. This is the point 0, 1. Actually, this can go on forever as long as 0, 1 is in the region. Okay? X in R. And you can take like this. And D is a subset. It has to be open, does not have to be closed. So this is your D. Because it has to contain this one. Okay? Other questions? Did I answer your question?
Mostly, I guess, then something else here. For X and R, you have to prove it's Lipschitz to show that it's unique and existence for the local Picards.
No, actually, as long as del F over del X exists, it's Lipschitz on that part.
Yes, okay, you're right.
Okay? And remember, t is contained between -1 and 1, right?
Yes.
And as long as del F over del X, so basically, del F over del X is 2x over t squared minus 1, right? And so basically that is Lipschitz since t is between -1 and 1. Okay? But you don't want to approach 1. All right? Okay. Any other questions?
That was helpful. Thank you.
Okay. So in this problem, I meant the corollary D. I meant the corollary here. So the rest follows similarly, like 4 is the same, okay? And so forth. All right. Any other questions? No. It does not fall apart. Let's say a t is between minus alpha and alpha, where alpha is less than 1. Where alpha is less than 1. Fixed number.
Sorry, I deleted that. I misspoke when I said that. If you're referring to my comment in the chat, you can ignore that. Sorry.
Okay. Yeah, it's a good comment. It's a good comment.
It was earlier. You had it less than or equal to. That's
Yeah.
sorry.
No. Yeah, I mean, remember your D must contain the initial conditions, correct? As long as it contains the initial condition, and then you're fine. Okay? Somebody asking, isn't it for problem 1, t minus 1 x prime equal x squared plus t? No, this is t squared minus 1. I'm doing t squared minus 1. Okay? I'm doing t squared minus 1. So this is part 4. Okay. All right. If you're going to use the other theorem, the Picard's theorem will be extremely difficult, as you said. All right. Okay. If you like, if you want to maximize g of t is 1 over t squared minus 1, okay? So if you look at the g prime equal to minus 1 t squared minus 1 times 2t minus 2, and that is minus 2t over t squared minus 1 squared. Okay, so t equal to 0, and so the maximum happen at t. So this is going to be less or equal to 1. So the maximum of this, so the maximum of 1 over t squared minus 1 is the whole thing can be, if you like, if you take alpha to be 0, less or equal to 1 over alpha. So this is less or equal to 1 over t squared plus 1. This is equal to 1 over alpha squared plus 1, if you like. And we know alpha is strictly between minus 1 and 1. Okay. No. This is wrong. This is when alpha is when alpha is the maximum. So this is gonna be less or equal to 1 over alpha squared minus 1, where alpha is close to 1. Okay. And you should show that it is Lipschitz and so forth. All right. If there is no questions, I'm going to continue with the lecture from yesterday. Okay, for the uniform asymptotic stability, if it is uniformly stable and there is a gamma, this one, positive, such that for each mu there exists t equal t mu positive, such that if xt not less than gamma at this point here, for t bigger than t naught, except x, if xt not less or equal to gamma, okay, then x of t, it can fluctuate, but there is a t such that for t bigger or equal to t naught plus this t, this always less than mu. So this is the definition of uniform asymptotic stability. And let me take x prime equal minus x as an example, and xt naught equal x naught. So this has a solution. X of t, t naught, x naught equal to x naught e to the minus t minus t naught. Okay? And this is for t bigger or equal to t naught. All right? And this solution exists for all time. So we need to show it's uniformly stable. So let epsilon be positive, then we want to find delta. So if x naught less than delta, we have x of t, t naught, x naught less or equal to x naught e to the minus t minus t naught, and that is less or equal to x naught, which is less than delta, and this will be epsilon if delta equal to epsilon. And this is for all t bigger or equal to t naught. So it's uniformly stable. So if we choose delta equal epsilon, we get that one. Okay. All right. Now we need to show it's uniformly asymptotically stable. All right. Now, for the uniform asymptotic stability, let me get rid of this pen. All right. So for the uniform asymptotic stability, okay, we must show there exists a gamma positive such that for each mu positive, there is t equal t mu positive such that x of t naught less than gamma for t bigger or equal to t0 plus t implies x of t naught x naught is less than mu. Okay. Since it's uniformly stable, set mu equal to delta equal 1. This is from the uniform stability. Sorry, gamma. And then for x t naught x naught, that is equal to x naught e to the minus t naught Okay. This is less than e to the minus t naught. Okay. Now we want this less than mu for t bigger or equal to t0 plus t, or e to the t bigger or equal to. All right. So we need to find that t. So, or e to the minus t less than mu. So now solve for t. Take algorithm Nash. This will be minus t less than ln of mu, or mu bigger than, or t is bigger than minus ln of mu. Okay, so we want this. We want for t bigger or equal to t0 plus t. Okay. So let's assume t equal. All right, so hence t mu equal minus ln of mu is positive, since mu is between 0 and 1. Okay, it's a small number. So we found a t. See, there is a t. There we go. We found it. We found the t. There is a t. Okay. So this shows the solution is uniformly asymptotically stable. I am introducing this concept just because we have a math student here, and they should be exposed to this stuff. And this is a graduate course in differential equation. It's mostly theoretical, and maybe this is the first time and only time in their lifetime we'll see a class like this. So I owe it to them that I should do this stuff. All right. Okay, and last time we gave an example last time where the solution is uniformly stable, asymptotically stable, but not uniformly asymptotically stable. Well, of course, this is an exponential function, so it's going to be uniformly asymptotically stable. All right, any questions? Any questions? All right. So I will stop here for that. I'm done with this section. All right. So now I am going back to section 4.2. So we're gonna look at x prime equal ATX. So we're gonna look at stability. And this is theoretical. That means we assume the existence of the fundamental metric solution. So we're gonna consider x prime equal ATX with xt naught equal x naught, and this is 4.21. Okay. All right. Where AT is an n by n matrix with continuous entry matrix with continuous entries on 0 to infinity. So we're only looking at t bigger or equal to 0. And we begin with theorem 4.2.1. So these are abstract theorem. They're abstract. It says, let phi t be the fundamental matrix solution. Again, fundamental matrix solution of 4.1. Then the zero solution, or what I mean is x equals 0, of 4.2.1 is parallelly stable if and only if there exists a positive constant m such that phi t less or equal to m in the node for L t bigger or equal to 0, be asymptotically stable, if and only if phi t goes to 0 as t goes to infinity. Okay, so take a look at the theorem first before I start proving it. Okay. So these are if and only if statements. All right. So I'm going to turn the board to do the proof here. All right. So proof. Let's go this way. That means let phi t be the fundamental matrix solution of 4.3. What is the equation called? 4.21 with phi of t less or equal to n. Okay? Now, the solution of 4.2.1 is xt t naught x naught equal to phi t, phi inverse of t naught x naught. Now, let epsilon be positive and need to find delta positive so that when x naught less than delta implies x of t naught x naught, which is phi of t, phi inverse of t naught x naught, which is phi of t, okay, phi inverse of t naught x naught, okay. And this is less or equal to m phi inverse of t naught delta, because x naught is less than delta. And this is equal to epsilon if we choose delta equal to epsilon over phi inverse of t naught times n. So this shows stability. Okay? Take a look at it. So we already know what delta is, what epsilon is. I mean delta in terms of epsilon. Any questions? Now we're going to go this way. We're going to assume xt t naught x naught is stable and show phi of t less or equal to n, or n positive. Okay? Well, now we know that xt t naught x naught is equal to phi t, phi inverse of t naught x naught, and that is So this is less than what would you like me to do? This is less or equal to x0, okay? Okay, what I can do here is I could say this is less than 1 if x0 is less than, if x0 is less than delta of 1 t naught. So basically what I'm doing is I'm set, so we're gonna, this is by setting epsilon equal to 1 from uniform stability, from stability. So since we know it's stable, let's take epsilon equal to 1. So we know that this solution is less than epsilon less than 1. If, okay, so what does that mean? That means phi t, phi inverse of t naught, x naught, okay, so let me rephrase this a little bit. So phi t equal phi t, phi inverse of t naught, phi t naught. I can write it like that, correct? Okay. Okay, so this is, I can play with it a little bit more. This is less or equal to phi t, phi inverse of t naught, phi of t naught. And this is less or equal to 1 over delta of 1 t naught, phi of t naught, and this is our m. So we got it, phi t less or equal to m. Okay? So all you need to show, if you want to know phi, show it it's bounded if you know the fundamental matrix solution, and that should tell you that the solution is a stable. But this is if and only if stable. I will prove B should be a little bit faster. Okay. So take a look at it. I mean, the proofs are in the book, really. And all right. So let's take a look at the second thought. Okay. All right. Okay, for B, we already know from A that the solution is stable. So now, so if I look at xt t naught, x naught, that is equal to phi t, phi inverse of t naught x naught, and that goes to 0 if and only if phi t goes to 0 as t goes to infinity. That's it. Okay. All right. Okay, so these are two things. I'm gonna prove one more theorem, and this is theorem, and then I'll look at an example. This theorem is gonna be, I'm gonna change it to 4.22. And I'm gonna say let phi of t be fundamental, then the zero solution is uniformly stable. Then the zero solution, x equals 0, 4.21 is uniformly stable if there is an m positive, okay? If and only if, this is if and only if there is a constant m positive such that phi t, phi inverse of s is less equal to m for t bigger or equal to s bigger or equal to s. So now it's the fundamental matrix and its inverse are less or equal to m. Okay? And the solution is basically the same. The proof is very similar to the other theorem, and you can look at it. All right? You can see it in the book. Just take a few minutes and to look at it before I do more things. Now, we're going to talk about the uniform asymptotic stability. And that is a little bit too strong. Okay. Are we all okay with this one? Can I change it? Can I put 3 now? Let phi t be the fundamental matrix solution for 1. Then the zero solution x0 for 1 is uniformly asymptotically stable if and only if there exists positive constant m and beta, if and only if there are constant m and beta positive such that phi t, phi inverse of s less or equal to m e to the minus beta t minus s for t bigger or equal to s bigger or equal to 0. So that is the difference between all the three theorems: stability, uniform stability, uniform asymptotic stability. Okay. And again, I need you to scan through the proof. So I'm going to give you 5 minutes before I do an example. I need you to scan through the proof, at least the one way. Okay. And these constant are positive, both of them, bigger than 0. So the fundamental matrix times its inverse at any time must be less or equal to some constant m exponential.
Sir, I'm not sure, but I think you're muted because I can't hear you right now.
How come I'm muted? Guys, can you hear me?
I hear you.
They can hear me. Okay. I don't know why I am muted. All right. I didn't do anything. Okay. So the uniform asymptotic stability require more from the fundamental matrix. There is a huge difference between the three theorems. So take a look at it, and I will be back with you to do an example, and I'll let you out early today. All right, let me take a look at an example. Let's take a look at, this is example 4.5. So we have x prime equal to 0 minus 2 over t squared, 1, 2 over t, x1, x2, for t is bigger than 0. Okay? I claim phi of t is t squared 2t, t and 1 is the fundamental matrix solution. So how do we do that? Now, don't ask me how I came up with it. The only reason I can tell you is we need to show that phi prime, if this is A, is equal to A phi. That's what we need to show. All right? So what is phi prime? Is 2t, 2, 1, 0. All right? What is A phi? Is 0 minus 2 over t squared, 1, 2 over t times t squared 2t, t and 1, and that is, if you multiply this, you get 2t. If you multiply this, you will get 1. If you multiply these together, you get minus 2. Or you get minus 2 plus 4. Oh yeah, if you multiply this with that, minus 2 over t squared times t squared give you minus 2. Plus 4t over t give you 4. Minus 2 plus 4 will give you 2. And if you multiply this here, you get minus 2 over t plus 2 over t, you'll get 0. There we go, which is phi prime. So it's a fundamental matrix solution. Any questions? Again, I ask you not to ask me how I got the fundamental matrix. Once the matrix A has T in it, everything is off the table. All right? We only know how to construct the fundamental matrix only when A is totally constant. That means every entry in A is constant. Otherwise, forget it. Any questions? All right. So now, what is the norm of phi? Let's take the absolute value of the entries, which is the sum of the absolute value of all entries of phi. So phi is phi of t, which is t squared plus 3t plus 1. And that goes to infinity as t goes to infinity. Then there is no positive constant m, so that phi of t less or equal to m for all t. Hence, by theorem 4.21, a x equals 0 is unstable. Okay? I can read. So I took the norm of the matrix to be the sum of all the absolute values, the entries. Then phi is t squared plus t plus 1, which goes to infinity as t goes to infinity. So then I come here. I said, then there is no positive constant m, so that phi t in absolute value less or equal to m for all t a positive. Hence, by theorem 4.21 part A, x equals 0 is unstable. Because the theorem is if and only if. That's why we can conclude that. Okay? Any questions? Okay, I'm going to do another example and then I will stop. Any question first before I go further? Okay? Let's take a look at another example. Remember here, phi t, phi s. So let's take a look at, this is example 4.6. X prime equal to 0 minus 2, 1 minus 2, x1, x2, and t is positive. Again, you can verify that phi of t equal to e to the minus t cosine t minus cosine t plus sine t sine t cosine t minus sine t is its fundamental matrix solution. Okay? You can verify this as we did before. Again, if you look, okay, if you look at phi, and this is gonna be phi t, this is gonna be less or equal to e to the minus t I'm gonna take the absolute value will be 1122. Will be 2246. So this less or equal to 6 e to the minus t. Add these together. This less or equal to 1, less or equal to 1, less or equal to 2, less or equal to 2. 2 plus 2, 4, plus 1 is 6. Okay? And then you can find phi inverse of s is less or equal to some number here, k e to the minus s. Okay? You can do that. Well, you need to find the inverse matrix for this one. I did it, but I didn't put it in my book. It's very complicated. But you can say some positive number k e to the minus s. So now, if you look at this phi t, phi inverse of s is going to be less or equal to 6 plus k. Sorry, this is a plus s. E to the minus t times e to the s, which is 6 plus k e to the minus t minus s for t bigger or equal to s. Okay? This should be s, t to the s, because you're looking at the inverse, because it's one of the determinant. I mean, this is a 2 by 2 matrix, by the way, right? You can easily do it. So maybe one of you can do it at home and let me know by tomorrow if what the inverse of phi inverse of s. So basically it's going to be one of the determinant. I mean, if you have a matrix A, B, C, D, you know, the inverse of that is one of the determinant times something here. I forgot. Okay? Because it's a 2 by 2 matrix, so it's doable. It's not hard. All right. So you see, so the zero solution, so the zero solution is uniformly asymptotically stable. Of this one is uniformly asymptotically stable. Okay? Any questions? You see, this problem is x1 prime equal x2, x2 prime equal minus 2x1 minus 2x2. This is what the system looks like. Okay? By this one, by the way, this one you can find, you can use a Puzzle algorithm. For this one, you can use Puzzle algorithm to find this fundamental matrix, okay? All right. Any questions? All right, I think I'm gonna stop here, and I'm meeting with somebody after you guys exit the meeting. Are there any questions before okay, I have 2. Okay, thank you. All right. Any question, guys? Okay, I'm gonna stop recording.